We could not cover thermal stress in the last class, so today I thought that I will take up thermal stress for a little bit of time. So when you have a member that is undergoing a mechanical stress as well as a thermal, okay? So for example, this is a member. This is an axial member, okay? And it's undergoing a load P. And then there is a temperature I delta T. All right. The member has its cross-sectional area as A, Young's modulus, elasticity as E. So what would be is its stress at any point that you take? Any point that you take, what would be its stress? Can anybody tell me? No?
Sir, at any point, we just have to see what is the displacement there. And then we can just first. So, I mean, did you ask stress or strain?
Yes, stresses.
Okay, so for stresses, we have to see the internal force there and then the area of cross section.
So what would be the internal force?
We have to write the equilibrium for that section and then try to find out the internal force there.
Okay, so some of you have already answered that it should be P by A. Now, what about the stress due to this change in temperature? Will not be there any stress due to this change in temperature?
There will be a change in length, sir. Because
Bend.
of the temperature. No, change in length, sir. Length.
There will be change in length, but won't there be any stress?
So stress, no, so like this temperature directly causes the strain, no, sir. Like it just changes the length, right?
Right, very right. So if you see us right up here, for a homogeneous and unconstrained or determinate body, no thermal stresses are generated. Okay. There won't be any thermal stresses because, as you said, thermal stresses are manifested by extension. And if it's free to extend, the stress will not generate. So contrary to this, if I have this problem, and you have a delta T rise, and there is a, let's say, there is a P force somewhere. Then obviously there will be a stress due to the temperature rise because the body is unable to extend, right? When it's unable to extend, the walls will put an external force, right? Those force will be generated because of the change in temperature delta T. So as long as your body is determinate, your structure is determinate, not only this rod, any structure that is determinate, right? You increase the temperature, that will just change its geometrical structure. It will reach, but what do I say? It will get into a new geometrical stability, but it will not raise any kind of stresses within its member. Stresses in the member only will generate if the structure is indeterminate. So thermal stresses are only for indeterminate structures. Okay. And next thing is another point that you should know, these thermal stresses only generates normal stress, not shear stress. Okay. So if the material is homogeneous, unless the material is not homogeneous, it's a composite material, then things may not be same because between the layer of composites, different layer of composites, there can be extensions of different length, and that can create some kind of friction between the material and they give rise to shear stresses, right? But generally, if you have a homogeneous isotropic material, if you increase the temperature, there won't be any shear stress that will generate. Okay, or there won't be any rotation, right? If there is no rotation, there won't be any shear stress generated. So thermal stresses give rise to two things that you have to note when you do thermal stresses. One, you have to look into whether the structure is determinate or indeterminate. Next, it will not give rise to any shear stress. It is only going to give rise to normal stresses, and that's, I think, in the stress-strain relationship, that this formula or the discussion is already been there. Okay, So the strain that is generated due to thermal as well as mechanical loading is going to be, this is due to the mechanical loading, and this is due to your change in thermal stress, change in temperature. Okay, so sigma xh by E is going to be mechanical strain, and this is your thermal strain, both are added up. And thermal strains we already know is it's alpha into delta T. Strain, total extension will be into L, right? Okay. So that's how it is. So when you need to find deformation about for the thermal, it's deformation going to be this is your mechanical deformation in L by EA, and then there will be a thermal strain into L as the thermal extension. Okay, clear? And delta T is always obtained by integral of alpha delta T dx. Your structure may not be uniform and thermal change may not be uniform all through your body. Then you have to do this integration. Yeah, there is a small problem that is solved here. I hope you have gone through this. Notes were uploaded last class. So this is the problem I was discussing. There is a bar which or a rod which has gone through a temperature rise of delta T. Now, since there is a temperature rise of delta T, this rod will try to extend, right? But since these walls are fixed, the bar will not be able to extend. And if it is unable to extend, what will happen? It will try to push the walls away, right? I'm assuming there is no buckling here, okay? So we are not assuming, so we are assuming very small deformation. So it will try to push the walls away by a little amount, but wall will not get away, right? So they will in turn provide a force to counterbalance it, right? So the wall will provide a force like this to the material. And that force will be related to how much rise in the temperature happened. Because this force is related to how much extension is trying to happen, and the thermal extension is related to the thermal temperature rise. So this RA and RB will relate to delta T. Okay, so what you do, this is an indeterminate structure. What you have to do, what you do is you release one of the boundary condition, move it away. So once you move one of the boundary conditions, now the material is free to extend, right? So one side is fixed. So the other side is free to extend. So the material will do, it will just extend. And while it extends, there is no stress here. Okay, but we have to provide an RB because we have removed this boundary. We cannot directly remove a boundary. We have to put a counterbalance force to remove the boundary, right? So this is the force RB that is applied. Okay, so delta or deformation due to rise in temperature is going to be alpha delta T L. Okay, and deformation due to RB or compression due to RB is going to be RB into L by EA. Compression meaning negative, and thermal extension was rise in temperature, so tensile. So this is your thermal extension, and this is because of the compressive load. Now, physically or in reality, the structure will not have any deformation at this point because it is bounded by the wall. Okay, so the deformation due to the change in temperature and deformation due to RB, the force that is acting to the wall, should counterbalance each other. Therefore, total deformation compatibility condition is delta B equal to 0, and that gives you delta T plus delta RB should be equal to 0. When you put it, you get your RB, and it is AE epsilon 0. Okay, once you know your RB, you can find thermal stresses. So your thermal stress is going to be here RB by A, right? Okay, that's going to be your thermal stress.
Sir,
Yes,
it's a small doubt, sir.
yes, small out.
Sir, in the case of like when we have a free end, this extension due to delta T will happen in that direction, no, sir. Like,
Yes.
so is it like, because delta T, unlike a force, it just extends the rod, so it can extend in both the directions, sir. So
Right.
so because of a fixed end at A, won't there be any RA like when it extends when there is a free end? So you're getting the question, sir.
Yeah, I got your question. So you mean, I'll tell you what you mean. You mean that the extension will be on the both sides. Why did I take only RB? That's
Yes,
what
sir.
you mean? Yeah.
Yes, sir.
Yes, true. So what will happen is the rod will expand in both sides, but the total expansion will remain the same, right?
Yes, sir.
So I am giving the total expansion to one side only, not on the other side. It will remain same. The force will come out to be same.
Yes, sir. So if we give the expansion in both directions, even if there's a free end, won't there be a thermal stress? Like here we gave the extension completely to B because there's a free end at B. But if we give it to both the ends, then because of the expansion at A, won't there be a thermal stress R due to RA? So
No, it is free to move on the other side, right?
yes, that's what I'm asking. So like, so if there is a free end, then the extension completely will happen at the free end. Also. Like,
Yes,
won't
only one
happen at
direction.
B.
Yes.
Okay, sir.
Okay. Now solve this one yourself. Okay, with a P force inside. How are you going to solve it? I hope it won't be difficult for you to solve. Only thing, the equation of this compatibility will change. So delta RB will change. Delta RB will be due to RB as well as due to P. So P is acting up to this point. So you have to understand that how to deal with that, right? You have to go by your methods that you have learned in your indeterminate structures for accelerators. There are a few salient points are written here. You have to go through them. What happens when you have a statically indeterminate structure? What is the compatibility equation? Okay, how do you find degree of static redundancy? So all these definitions are given here, formal definitions which you have to read. And then how do you solve in a force method or flexibility method, and how do you solve in a displacement or a stiffness method? These step-by-step things are all given, and what are the different things that you have to do while doing this, or you have to know, are all given. Please go through them. Okay, general procedure for solution for indeterminate structures. You have to free one of the forces, or you have to free one of the degree of freedom, and then put a force and then solve it. All those details are here. And let's go to stress concentration. We discussed about stress concentration from long time and it was pending. We said that whenever there is a change in cross section, right, like this, there is a sudden change in cross section, or whenever there is a hole between a member, within a member, right? In those cases, or where there is a force acting, in those cases, the forces near these boundaries, the boundary of the hole or the change in the cross section near these boundaries, are not going to be uniform. They're not going to be your average stresses. The stresses will be quite higher than your average stresses. So we call something we have that is called stress concentration factor, K, which is the ratio of sigma max by sigma average. Sigma average is your normal stress that you get from your calculations, right? So at any point, if you want to find the maximum stress that is going to happen, you have to multiply that stress with this stress concentration factor. That's why stress concentration factors are very important, because it gives you the maximum stress that can happen near any change in cross section, near any hole in a material. Okay. All right. So what is this stress concentration factor depends on them. As you have already understood that we told that when there is change in geometry or when there is a hole, there is a stress concentration that comes in. So stress concentration is going to depend on the change of the geometry. So it's a geometrical factor, or it's going to depend on the hole. So that also a radius of the hole probably. So that's also a geometrical factor. So stress concentration is a geometrical property. It's not a material property, right? So it is independent of material. So whatever material you have, your stress concentration factor is not going to change. Okay. All right. Therefore, stress concentration factor is independent of material properties and depends only on the specimen geometry or type of discontinuity. Okay, let's look at this figure. You will get this kind of figure in the books, the one where there is a change in cross section, right? Please note that the change in the cross section is not exactly rectangular, not exactly 90. There is a slight curvature that is given here. Same slight curvature is given here. Okay, the curvature, even if you don't give in your design the curvature, your design may have structural change like this, a rectangular. When you construct the material or when you manufacture material, the engineer will definitely provide you a curvature here. The reason for providing the curvature is that the stress concentration reduces a lot if you put a little bit of curvature. Okay, otherwise it will be a very high stress concentration factor, and those will be starting fracturing or getting cracks from these corners itself. All right, so you have to look into that part also. So stress concentration factor, as I said, depends on the width of the material, right? and the reduction in width, that means the final width, that is which can be written as h. Okay, and the radius of curvature that you have here. So radius of curvature by h, that means this curvature by this h is on the x-axis and your stress concentration factor K is on the y-axis. And you see, you get different curves for different values of W by H ratios. Okay, so how big to how small you are becoming, right? So you see all the stress concentration are quite high when your radius of curvature R is almost near to 0, right? And it goes down as you go, it comes down very fast as you have little bit of curvature. So you need to, as an engineer, provide a little bit of curvature here so that your stress concentration factors comes down. When your stress concentration factor comes down, your sigma max by sigma average comes down, right? So your sigma max will not be very far away from your sigma average. Okay, and any value, which is lower than 1 is okay. All right. So now when you have a hole, same thing. When you have a hole with or a diameter is 2r, it will also depend on that. So it's r by w here. W is the full width. R by w, and this is a stiffness factor, concentration factor. Okay. So that's also a curve like this. What you do is, when you design your structure, you know your R, or you need to, let's say, find R. Okay. So you got a sigma average at this cross section or at this cross section. You got a sigma average at this cross section. Okay. Once you know the sigma average, you know your maximum sigma y or yield, design yield. You know that. What you have to do is you have to find R such that your sigma max is lesser than your design yield. So let's say that R is 0.4. Okay, so you go to 0.4 and then go and select the particular W by H factor. Let's say I am coming here. So my maximum stress is going to be, so I have to give R, okay, the stress concentration factor is 0.4, right? So I said here, so I go here, I come to this value. So you have to give a curvature of 0.3 radius at this point, okay? That's one way of going. The other way of going is finding K and finding sigma max if you know the radius at the curvature. Yes, so we are in torsional member and this date has to change. Today is 27th of September. And that's going to be 2021. Okay, what we have is same as what we had in the Excel members. We have to learn a few terms here. What is a torque twist relationship? What is a stress strain in a pure shear conditions? Then uniform cross sections, non-uniform cross sections, like in Excel members, and then statically determinate structures we have to solve, and then look into stress concentration and strain energy in torsion. Most of the part will be very easy and similar to your Excel members. Only thing is we need to learn a little bit. We need to pay a little bit of attention in the first part of it, where we deal with torque and twist relations. A few example of torsion. A lot of torsion. Torsion is hugely used in the industry because it transfers power from one side to another side, right? So from one part of a mechanical system, it transfers power to another part of the mechanical system. So it is used heavily in cars, right, where you have a steering column and you have this steering. So when you rotate the steering, things change internally using gears, right? So this rod, we call it shaft, is going to transfer your rotation from here from the driver to the mechanical structures, right? They are also used in wind turbines. So these wind turbines, these guys will rotate, and once they rotate, the shaft actually rotates through the bearing, and then that is converted to generator. Here is a car where the wheel is moving. So this is a shaft. We also use torsional member in analog clocks, which were used on old days. Many of you may have in their houses also analog clocks where we twist and we store kinetic energy or store potential energy in this torsional spring, and then the spring slowly releases energy and your clock turns. So this is a representation of a torsional spring. So this is called a linear spring, which is mostly in axial direction. and there is this spring which are called torsional springs. So this they restrict movement. So the relationship M is given by K into theta. Here the relationship P is equal to K into delta. Right. Okay. We also use torsions in our everyday life to take care of any wet clothes. You want to drain water away from wet clothes, you just use torsional mechanism to do that. Okay. So these are all various, applications. There are many, there are many applications of torsion. A few of them are here. Right. So when we talk about torsions, we need to look into sign convention. This is very important, and this is where a lot of us make confusions. A torsion is represented by double arrow, like a moment. Okay. And you have to use the right hand rule or corkscrew rule to find the direction of torsion. Okay. So for example, if I rotating this structure here, the rotation is in this direction, and you put your right hand thumb rule. So the direction of torsion vector is this. Similarly, if you rotate this one in this direction of torsion vector is along that direction. Although the direction of torsional vectors are opposite to each other, okay, we call both the torsions as positive because the torsion vector is going away from the material. Okay, if the torsion vector doesn't go away from the material, then it might be negative. So in the sense that both this one and this one is a positive torsional vector. Both this one and this one are positive torsional vector. This one is also positive torsional vector because they are all going away from the cross section, right? This is the cross section is going outside. This is the cross section is going outside. But if I have this one like this, so I'm rotating this part in this direction, right? No, not that direction. If I rotate that part in this direction, for example, this one, I'm rotating this direction. So my torsional vector is this. Okay. This is my torsional vector. Then this is a negative torsion, a negative twist. So we have to be careful with this. Okay. Right. So the objective is it is positive when it acts as shown, complying right hand corkscrew rule. Okay. I will tell you it is always positive when it acts away from the cross section. Right. So for one cross section it will be positive, for the other cross section it can be negative. So please pay attention that side. Okay. Now look at this picture. Yes.
This torsion vector is the arrow, no? So like which is found by the rotation which we apply, right?
Yes, double arrow.
It is not the it is not the circular thing, right? Like circular arrow.
Circular arrow is what we give. Okay, in mechanics we will represent them with circular arrows only. Right? You have to assume that circular arrow is going from either clockwise or anti-clockwise, and then you have to put your thumb and see whether it's inside or outside. Okay, your mechanics problem will always show it in terms of this or in terms of this, not in terms of this. Very few problems you will see they are in terms of this. Okay, in mechanics the representation will be with the circular arrows, either clockwise or anti-clockwise. But you have to then put your thumb and rule and right hand thumb rule, and then you have to see whether it's positive or negative. Okay. Right.
Okay.
A few examples of torsions when you have a member here. So what we do, our objective of this course is to understand only circular cross sections, that means rods, okay, or not anything other than circular rods, because there is a reason to it. When you have anything other than circular rods, the analysis of torsion becomes very complicated. That's what is shown here. So you have a rod, right? This is a rod, and you have given a torsion T dash here. Okay. So what happens? The body will start, you put a lot of lines here, and if you put a lot of lines, this line will start getting twist. they will start twisting. Because the cross section here, which was like this, 90 degree, will not remain 90 degree here. Obviously, they will go like that, right? Some twist. They will stay 90 degree, but it will make an angle. What happens, that angle between two lines here will not change in the deformed configuration also. So a 360 degree, so the total 360 degree will remain total 360 degree here. So if you see, look at the cross section only, if you look at only the cross section, you won't find any difference when you give a torque. But if you put two lines here, you will see the lines have moved. Okay, that's what you are going to see. But if you don't put lines, you will not see any difference, because the circular cross section remains circular before and after twist. So that's one of our assumptions here. Cross sections remain plane and circular before and after twist. So it remains plane also. That means a cross section that is in this plane will remain at that plane only. It will not deform out of it. In case of non-circular cross section, there is something called warping happens. That means the planar section doesn't remain plane. They go inside in some portions, it will go outside in some sections. So if you see this picture, this line that was vertical before is no more a straight line, right? What happens, these corners, they will either go inside or they will come outside. So you will see that the plane section that was here before is no more a plane. It will be something like this. So some portions will go inside, some portions will come out. This is called warping, and that you cannot analyze using strength of material understanding. For that, you need advanced solid mechanics to understand. You have to model it properly. And in many cases, even for simple geometry like squares and rectangles, you can find out. But you make the cross section a little bit complicated. For example, ellipse. It will be very difficult for you to find warping. Just I have something like this. It will be very difficult for you to find its warping. Okay. So, torsion is a bit complicated when your structural materials are of complicated geometry. But for our case, it's only a circular geometry, and it's very simple for us to circular geometry. So few assumptions that are made here, that the circular cross section is a hollow or a solid shaft. Okay, you are not looking into anything else. So you are looking only into axisymmetric assumptions. Only pure shear is considered, so there is no combination of shear and normal. Okay. Cross sections remain plane and circular before and after twist. This is I have explained already, and this is very important assumption. Rotations are assumed to be small and within elastic limits. So we are not going into plastic zones. Under twist, neither the length of the bar nor the radius will change. So it will neither increase in length nor its radius will change. So there is no increasing length, and therefore there is no change in radius. Why is there no increasing length? Because, as I said, a plane section will remain plane. So there is no twist, right? So there is no warping. There is only twist, there is no warping, and therefore change in length is not there. But that is not true for members that are non-circular, because some of them will go inside and some of them will come outside, some portions. And therefore, in some portions, the length will increase and some portions, the length will reduce. Okay. All right. We need to understand few things when we deal with torsion. One of them is angle of twist. What is an angle of twist? Okay. Angle of twist is this phi BB or phi AA is called angle of twist. This is your angle of twist, phi. What is phi? Suppose I have a rod that is fixed to the wall here, and I give a twist here. Okay, what will happen? If I have drawn some mesh of circular or horizontal lines here, and if I have chosen only one portion of cross section, let color it better. Which will this color work here? Ah, fantastic. If you look at this cross section, which was almost like a rectangle before deformation, will not remain rectangle after deformation. It will become a rhombus kind of thing, twisted parallelepiped. Okay. Why is like that? Because all the straight lines will not remain straight lines because of the twist. So this point will move to some other point, but this point is fixed, so that will remain same. So it will become a inclined sort of line like this. So this straight line, which is horizontal, will not remain horizontal after bending, after twist. Or all these lines will move parallel to each other because circle is going to remain circle. So these circles will not change. They will remain circle because of our assumption. So they will remain circle before and after twist like this. And therefore they are going to only linearly move. So the line which was like this has now become this. So this angle is called phi, the angle of twist. Okay. I will tell again, the angle that is made by its initial straight line with the inclined line is called the angle of twist. And this angle of twist is going to change for each cross section because it is 0 here, like our deformation in axial member. It is 0 here and it is maximum at the free end. So angle of twist is a function of x. Okay. All right. So every cross section will have its own angle of twist. Right. And that will be depending on its position. That will depend on its x location from the fixed end. All right. Now look at only one of the cross section that we have. Okay, that is a circular cross section, right? Okay, so I'm taking two cross sections here. One is BB cross section and one is AA cross section. Okay, so the BB cross section is shown here. And AA cross section is shown here. So this is your BB cross section, and as you can see, the BB is near to your fixed end, so it will have less twist, whereas AA is far away, so it will have more twist. So perpendicular line QP before deformation will remain perpendicular, but will rotate a little bit, and that rotation is given by phi BB, the delta of phi BB. Similarly, at cross section A, you will have more rotation, and that is represented by delta phi AA cross section. Okay. Now, if the point here N has moved to N dash and point M has moved to M dash, similarly point Q has moved to Q dash and P has moved to P dash, I can have this relationship. N dash is equal to M dash because this point and this point is going to be same because it's only a circular rotation, right? It's going to be R d phi AA. So this is your d phi AA. So it's going to be radius into d phi AA. Similarly, PP dash and QQ dash is going to be R into d phi BB. Very simple relationship because we are assuming very small angle change, right? Now look at this picture. Okay. We have already talked about these two pictures and we have said that N dash is going to be R d phi and N1 N dash is going to be rho. So, okay. Now look at this picture. This is one of the cross section. Let's say this cross section is this. And now what you have is you have this straight line, this perpendicular line changed to another perpendicular line, but with a little bit of rotation. So N has moved to N dash and M has moved to M dash. Okay. If I look within the material, within the radius here, so that's my maximum radius, R. If I look another circle which is inside it, but at a radius of rho, it has moved only from N1. So its only the original location was N1. It has moved to N1 dash, right? Now, this is given as this arc is given by R d phi. So this arc will be given by rho d phi, right? Because the radius is rho. Phi is constant here. Okay. So as you go inside the material, your strain again reduces, or your total deformation reduces. So at the center point, your deformation is going to be 0 because R is 0 there. Okay, so the maximum deformation or maximum strain is going to be at the top layer. For the gamma, how are you going to represent that with shear stress? So this was my member first. So that was my member geometry first, and that has been now this way. So it has moved like this. What is your shear strain? Shear strain is this change in angle, right? Shear strain is going to be this change in angle. So if this is your dx, shear strain is this by dx, right? It is going to be this by dx. Now dx doesn't change. What is this? This is the maximum value of the change here. So this is this guy, n dash. So it become r d phi. So gamma max is given by r d phi by dx. So gamma anywhere within the material will be phi d phi by dx. Is that clear?